Hello everybody, this is Gordon. We're starting a problem set in atomic weights, molecular weights, and moles. The idea is here, Avogadro's number 6.022 times 10 to the 23rd. That is the number of units of something in a mole, like a dozen is 12. That number is a mole. It's like a dozen, only bigger. The idea is that a mass of an element or a molecule is so many atomic mass units, then 1 mole of the same element or molecule weighs that number in grams. We're asked to find the first question, the molecular weight of sulfuric acid. Formula is H2SO4. And so taking the numbers from the periodic table, we have 2 hydrogens, so 2 times 1.01 times, 2 times 1.008 plus 36.064 plus 4 times the weight of oxygen, 15.9994. Do the arithmetic and come up with an answer of 89.078 atomic mass units. The second question, we're asked to find the number of grams of H2S contained in 0.400 moles of H2S, and also how many grams of hydrogen and how many grams of sulfur are present. We have the relationship between moles and mass. We know 1 mole of an element or a molecule is that weight in grams. And so if we know the molecular weight of H2S, we'll know how much mass 1 mole is. And so using numbers from the periodic table, we come up with a molecular weight for H2S of 34.080 AMU, which means 1 mole of H2S weighs 34.080 grams. And so we multiply that by the 0.4 moles that were given. And using 34.080 grams per mole, the moles of H2S cancel out, numerator and denominator, and we're left with 13.63 grams of H2S. Going back to our given 0.400 moles of H2S, we know that for every 1 mole of H2S, there are 2 moles of hydrogen per mole of H2S. That tells us that in the sample that we have, there are 0.8 moles of H2S. If we multiply that by 1.008 grams per mole, then we come up with a numerical value of 0.806 grams of hydrogen present, knowing that we have 13.63 grams of H2S in the 0.400 moles and 0.806 grams of hydrogen present. We subtract the two to arrive at 12.82 grams of sulfur present in the 0.4 of a mole of H2S. Third question, how many moles are there in 9.54 gram sample of SO2? Atomic mass of sulfur, 32.064 AMU. Oxygen, 15.999 AMU. The first thing we want to do is come up with a molecular weight, or molecular mass for the molecule that we're working with. So it's 1 times the molecular weight of sulfur plus 2 times the molecular weight of oxygen. When we do the arithmetic, we come up with a molecular weight of 64.063 AMU. That means that 1 mole of SO2 will weigh 64.063 grams. And so to determine the number of moles, we have 9.54 grams of SO2. We know that 1 mole has a weight of 64.063 grams. We multiply these two numbers together, we end up dividing 9.54 by 64.063. The grams of SO2 in the numerator and denominator cancel out, and we're left with 0.194 moles of SO2. And that's the answer. Our fourth problem, naturally occurring carbon has C12 with an atomic mass of 12.0000 AMU and C13 with 13.0034 AMU. What percentage of these are in a sample of carbon with an atomic weight experimentally determined to be 12.0112 AMU? Good question. This is part of the carbon dating scene, and we start with letting X equal the percent of carbon-13 present. Then we can say that the atomic mass of the sample that we have is equal to a certain percentage of C12 and a certain percentage of C13. So it'll be the atomic mass of C12 times 100 minus X, which is the percent of C13. Divide that by 100 to make it a percent. And we add X times the atomic mass of carbon 13 divided by 100 to make it a percent. And when we crunch the numbers a little bit further, we have 12 plus 0.01034x is equal to 12.0112 atomic mass units. X then becomes 1.109%. It's carbon 13, and that means percentage of carbon 12 is 98.891%. And that's that problem. Problem number 5, a 1.5276 gram sample of cadmium chloride yielded 0.9367 grams of cadmium by reduction. If chlorine has an atomic weight of 35.453, what is the atomic weight of cadmium? The idea here is to find the number of moles of chlorine. We can then use the relationship that's expressed in the molecular weight to come up with the number of moles of cadmium present. We know how much weight there is, so if we know the number of moles and the weight, which is given as 0.936, we'll be able to back calculate and come up with the atomic weight. And so the first thing to do is to find the number of moles of chlorine that were present. We started off with 1.5276 grams of cadmium chloride, and the reduction resulted in 0.936 grams of cadmium. That means that present were 0.5909 grams of chlorine. If we take that number and multiply that by a relationship, 1 mole of chlorine over 34.453 grams of chlorine, we find that our sample initially had 0.01667 moles of chlorine. We know that because of the molecular formula for cadmium chloride, there are 2 moles of chlorine for every mole of cadmium. And so using that relationship, we can determine that we had in our initial sample 0.008333 moles of cadmium. And then finally we can use the bottom statement, 1 mole of the element or molecular weight at X grams, the relationship. We had 0.9367 grams of cadmium, represents 0.00833 moles of cadmium, which gives us an atomic mass of 112.14 AMU. And that's the set. Thanks for watching.